When Markowitz first introduced portfolio theory, investment managers were very excited. It greatly simplified their lives. If all they had to do was invest in a combination of T-bills and the optimal portfolio, for each individual investor, all they needed to do was work out their level of risk aversion, and that would determine how much they invest in T-bills and how much they invest in the optimal portfolio. But as they came to apply Markowitz's model, what they found was that they were having problems. Specifically, the problems were related to their estimates of expected returns. That's what we're going to deal with today. In the last video, we calculated expected excess returns using historical data and using the CAPM. And based on those two measures of expected returns, we then calculated expected excess returns, and then we solved for our optimal portfolio, with or without short selling constraints. But let's take a look at our estimates of expected excess returns. Consider Intel. Based on the historical approach, Intel is expected to earn slightly negative returns each month, whereas the CAPM says that Intel is expected to earn over 1% per month. We could also look at Amazon, expected to earn 3% per month using the historical approach, but only 1% a month according to the CAPM. We observe differences for all the stocks. For AEP, the differences are relatively small, but there are differences. And what practitioners found was that even small differences in expected excess returns lead to huge changes in the weights. And we can see that in the next two columns. Look at the weights for Intel. The weights have gone from highly negative to fairly highly positive. Now you may say that's reasonable because we've had a large change in the returns. The expected returns went from slightly negative to being almost 1.5% per month. But let's look at AEP's weights. For AEP, the expected returns changed from 0.3% a month to 0.6% per month. Look at the change in the weights. We've gone from minus 20% to plus 30%. And yet we've only had a very small change in AEP's expected excess returns. In contrast, for Amazon, the expected returns have dropped from 3% per month to 1% per month. And we see a very large shift down, even though, according to the CAPM, Amazon is still earning the second highest expected returns. We now only hold 3% or 4% in Amazon, relative to almost 70% before. If you were the practitioner trying to allocate billions of dollars, would this table be comforting to you? If your top quantitative analyst said, here's what happens when we use these two different estimates, would you be comfortable using either of the estimates, or would you be concerned? Most investment managers were very concerned, and it actually caused a lot of Markowitz's ideas to fall out of favour. Let's think a bit more carefully about our measures of expected returns so far. We've seen that we could use the historical returns, and this is based around the idea that returns in any month are going to be equal to the expected returns for the stock plus a random error component. The average returns can be decomposed into the expected returns component and the noise component. And on average, the noise component equals 0. So we're left with a measure of expected returns. The problem with this approach is that past performance doesn't necessarily predict future performance. We know that firms change considerably over time. For example, in our sample we have Amazon. Amazon has grown rapidly over the past decade, but its growth is likely to be slowing down. The same could be true for Intel. The second approach we adopted was the CAPM. CAPM predicts that expected returns are equal to the risk-free rate plus beta times by the expected market risk premium. But the betas that we use in our formula, they are estimates, and the estimates are based on historical data. But the betas may change over time, and so using historical estimates of beta may not be a good measure of future expected returns. For example, we have in the 90s, Amazon was a very small, high-growth firm. It actually had a very high market beta, sometimes in excess of 3. Now it's a larger firm and its beta has been reduced considerably. So using a beta of 3 would have been inappropriate for Amazon going forwards. Another problem with the use of betas is that they are estimates, and we saw that there is a lot of uncertainty surrounding these estimates. When we calculate expected returns, we don't take into account this estimation uncertainty, and yet we should. Both these approaches, the historical returns or the CAPM, are historical. They look at past data to estimate future expected returns. Really what we want is a forward-looking measure of expected returns. And probably the best measure would be the market's estimate of expected returns for each stock. Not just one person's view, but the market's estimate. So that's a weighted average of every person's view. That would be a good estimate of expected returns. The problem that faced practitioners was how do you work out what the market's estimate is of expected returns for each stock? Two researchers who worked at Goldman Sachs, Black-Litterman and Fisher-Black, came up with an idea. And the idea was based on the investor's utility maximization problem. We saw that all investors try to maximize their expected utility. And their expected utility is defined by this utility function. And what we solved for was the weights. We wanted to find the optimal weights that would maximize expected utility for an investor. And we saw that our solution was that Z is equal to S inverse, where S is the variance covariance matrix, times by the expected returns minus the risk-free rate. And we know that Z is equal to 2 times lambda times by W. So W was equal to 1 over 2 times by lambda, all multiplied by S inverse times by the expected excess returns. Now the assumption made by Black and Litterman was that at any given time, in equilibrium, the market portfolio is mean variance efficient. Why would they say that? If we think about our model, all investors are maximizing their expected utility. And we know that all investors are going to hold some combination of T-bills and the optimal portfolio M. If all investors, when they invest in risky stocks, hold the same optimal portfolio, what's the market portfolio going to be? Well, the market portfolio is going to be the optimal portfolio. On our graph, we have risk and we have expected returns. We have our T-bill rate. Here we have our feasible set of investments. The optimal portfolio is also equal to the market portfolio. And we know it's an efficient portfolio because it's lying on the efficient frontier. With that insight, Black and Litterman then thought about reversing the problem. We observe the weights. These weights for the market are observed. We can see how much we should invest in each stock, because we can see how big a chunk it is of the market portfolio. This was a really clever observation. They turned the problem around and said, we observe W, maybe we can back out what the expected excess returns are for each stock. So they said, let's not estimate this. We don't want to use estimates. Let's try and solve the problem to find an expression for the expected excess returns. So originally we were solving to calculate portfolio weights, but we can observe the market weights and we know that all investors are investing in the market portfolio because it's the optimal portfolio. That means we don't need to solve for weights because we've observed the market weights. Instead, we can solve for expected excess returns. Here's the investor's problem. We're maximizing expected utility. And that's going to be the function for expected utility is W transpose times by mu minus RF minus lambda times by W transpose S times by W. And if we solve this problem for the investor, we get that mu minus RF minus 2 times by lambda times by S times by W is equal to 0. We know that expected utility is maximized when the slope of the function is equal to 0. We can rewrite this to find an expression for expected returns. So we get mu minus RF is equal to 2 lambda times by S times by W. We have an expression for expected excess returns for every stock. What we need to think about now are, do we observe lambda, S and W? Well, we know W. W is going to be the market weights. But what about lambda and S? Black and Litterman showed that portfolio weights are not very sensitive to the variance-covariance matrix. They found that changes in the variance-covariance matrix didn't lead to large changes in the portfolio, in the optimal portfolio weights. So they recommend using historical data for the variance-covariance matrix. What about lambda? Lambda is a measure of risk aversion, and we're going to look at the average market level of risk aversion. So not any one individual's, but the average across all individuals, because we want to back out the market's best guess of expected returns for all the stocks. So the risk aversion level is going to be equal to the market's risk aversion level. Now, how do we extract a value for lambda? Well, we know what the average excess returns on the stock market are, and we know the risk from investing in the stock market. And if the market is mean variance efficient, we can estimate the price of risk lambda using the following formula. Lambda is going to be equal to the expected excess returns on the market divided by 2 times the variance of the market returns. Black and Litterman show how you can derive this formula, but for our class there is no need to derive this formula. We're just going to use this formula in Excel. It will not be necessary for exams. Well, let's go do this in Excel. Let's see if we can calculate the market's guess of expected excess returns for the 5 stocks we've been looking at throughout this class. First, we need to get data on the stock market. One place where we can get data on the stock market is at a researcher's website. In the past we've dealt with papers by Fama and French. Well, Ken French provides a data library on his website. And he has lots of data. Here I've come to his data library webpage. And we have data for the Fama French factors. We have data for the 25 portfolios formed on size and book to market that we've been using in class. We also have data on momentum and on industries, which you've been using in your homeworks. To get market data at a monthly return horizon, we can download the Fama French factors dataset. If you look at the details for this dataset, we have an estimate of excess returns on the market. And this is all firms in the NYSE, Amex and NASDAQ. I downloaded this data earlier and put it into an Excel spreadsheet. Here is the data for the market returns over the last 80 years. We have the market returns, we have the risk-free rate, and we have the excess stock market returns. What we need to do now is calculate our estimates of lambda. First, we need to calculate average excess returns. And that's going to be equal to average. And then let's select the excess stock market returns. Close brackets. The variance, VAR, is equal to the variance of the raw stock market returns. Let's select the raw stock market returns. Close brackets. We can now calculate lambda. We have the formula listed here. Lambda is going to be equal to the average excess returns on the market divided by 2 times by the variance of the market returns. Let's hit enter. And we get a lambda of approximately 1.1. This estimate of lambda is based on the last 80 years of data. But maybe you think that's not realistic. Maybe we should be looking at just the last 50 years of data. We can do that as well. Suppose we want to look at, say, 1950 onwards. So we take out the effect of the Second World War and the Great Depression. We could do that. We're just going to use the same formulas again. So equals average. Then we select our excess returns. But we only select the excess returns since 1950, which I know starts in cell D284. We can also calculate the variance, which is going to be equal to VAR. Then we're going to go B284 to B973. Press enter. We can now enter the formula for lambda, which is equal to the average excess returns divided by 2 times by the variance of the stock market returns, which gives me a value of lambda of approximately 1.8. Which lambda should we use? It's difficult to say. This is where we need to use our judgment. You may think that using 80 years of data is not good because we include the Depression, the Great Depression, and we include the Second World War, both of which had profound effects on the economy. So we could use data from 1950 onwards. Maybe that's a better estimate. But some people view the last 50 or 60 years in the US to be something of a miracle. The amount of growth that we have had in the US has not been matched by any other developed country over the last 60 years. So maybe estimates based on the last 60 years will produce a lambda that is too high, because we've had very high returns on the market without that much risk. I'm going to use a value that's between 1.1 and 1.8. I'm going to pick 1.5 as my value for lambda. But remember, we could change that. The higher the lambda, the higher the compensation we require for taking risk. Now let's see if we can calculate implied excess returns. In this spreadsheet, we have the inputs to calculate implied equilibrium excess returns. We have our 5 stocks, Intel, AEP, Amazon and Merck. We have lambda, which we've set at 1.5. And we know from our previous spreadsheets that we have a variance-covariance matrix called S. So we have all the data we need to calculate implied equilibrium excess returns. The first thing we need to do is calculate the market weights. Recall that Black and Litterman say that in equilibrium, the market portfolio is mean variance efficient because it's the optimal portfolio for investors. And so we observe the market weights. They're the optimal weights. To calculate the market weights, we need to find the market capitalization of each stock. We then need to sum up the market caps of all the individual stocks to find the total market cap. In this example, we're going to assume that the total market consists of just these 5 stocks: Intel, AEP, Amazon, Merck and ExxonMobil. And I went into Yahoo Finance and downloaded the market capitalization data that is readily available in Yahoo. Here is the market cap for the 5 stocks, and this is in billions of dollars. We can see that ExxonMobil is comfortably the largest, followed by Intel, then Merck, then Amazon, and then AEP. To calculate the market weights, we first need to calculate the total market capitalization, which is going to be equal to the sum of the individual market caps. We can now calculate the market weights, which is going to be equal to the market cap for Intel divided by the total market cap. Let's use the dollar sign so that as we copy the formula down, the total market cap does not change. We've now calculated the market weights. We can check that we've done the calculation correctly by calculating the sum to make sure that the weights add up to 1. And the weights do add up to 1. Before we calculate implied equilibrium excess returns, let's name some cells and ranges to simplify the problem. We have the price of risk, or lambda. We've set it to be equal to 1.5. Let's name this cell lambda so that it's easy to refer to. We'll also need to talk about the market weights we also need the market weights for our formulas. Let's select the 5 cells with the market weights and name the range W underscore market, MKT. We're now ready to calculate implied equilibrium excess returns. How do we do it? We're going to use this formula. Implied equilibrium excess returns are equal to 2 times by lambda times by S times by W. So select the 5 cells where you want the implied equilibrium excess returns to be put and type equals 2 times by lambda times by, and now we need to think about S times by W. This is matrix multiplication again. So we need to do M mult, open brackets. The first array is going to be S, and we're multiplying that by W, where W is the market weights, which we've just labeled W underscore market. Let's close brackets and press Control, Shift and Enter. We've calculated implied equilibrium excess returns. But it's useful to check whether our intuition is correct with regards to lambda. We know that if we increase lambda, that means we're more risk averse. That means we should require higher excess returns to compensate us for bearing risk. Let's just check that everything works according to our intuition. Suppose we change the value of lambda to 2. When we hit enter, our formula will automatically update our estimates of implied equilibrium excess returns. And you can see that as we increase the price of risk, so the implied equilibrium excess returns also increase. That's good, that's consistent with our intuition and shows we've got the formulas right. Let's set the price of risk back to 1.5. How do these implied equilibrium excess returns compare to the historical estimates or the CAPM estimates? Looking at this table, we can see that the CAPM estimates and the implied excess returns seem to be broadly similar. If we look at which stocks have the highest CAPM excess returns and the highest implied equilibrium excess returns, we have Intel and Amazon. We see that returns for Merck are similar for both the CAPM and the implied. The returns for ExxonMobil are also fairly close. The only one that changes substantially is AEP. What about the historical excess returns? First, let's look at Intel. Both the CAPM and the equilibrium approach imply that Intel is going to earn expected excess returns of approximately 1 or 1.3% per month. But the historical estimate says actually Intel is expected to earn minus 0.3% per month. That's very different. Similarly, if we look at Amazon, the historical excess returns suggest that Amazon is going to earn expected excess returns of over 3% a month, or 36% per year. Amazon is a large company. Is it really likely they're going to earn expected returns going forwards of over 36% per year? It doesn't seem reasonable. And it's very different from the estimates based on either the CAPM or the equilibrium approach. There are also pronounced differences for Merck and ExxonMobil when we use the historical excess returns. So overall, it looks like the CAPM excess returns and the implied equilibrium excess returns yield fairly similar results in this example, while the historical excess returns yield very different results that are not consistent with the CAPM or the implied equilibrium returns. We still don't know which are more reasonable. Practitioners are also still debating how you should estimate expected returns. Some advocate the use of the CAPM, others advocate the use of implied equilibrium excess returns. There are entire books dedicated to estimating expected returns. There are advantages and disadvantages to both approaches. That's all I want to cover in this video. See you in class.